In 11.4, we're going to start our discussion on probability. Okay, starting out with some vocabulary first. An experiment is any occurrence where the outcome is uncertain. For example, tossing a coin. When you toss a coin, you're not sure what it's going to land on. The sample space is the set of all possible outcomes. I've written it here in set notation, so notice the sample space equals H for heads, T for tails, if you were flipping a coin. So those are the two things that could possibly happen. An event, which we're going to capitalize with the letter E there, any subset of a sample space. So an event could be it landing on heads. Another event could be that it lands on tails. Okay, theoretical probability only applies to situations in which the sample space only contains equally likely outcomes, all of which are known. So theoretical means that we're doing this in theory. We're figuring out what should happen based on the information that we have. It's only going to be used for situations where everything has an equal chance of happening. Okay, in other words, we're forming a theory based on the information that we have. So one example, the formula. If an event E has N of E, notice that this is some notation from Chapter 2. Okay, N of E was the cardinal number, or the number of ways E can happen there. It has N of E equally likely outcomes, and its sample space has so many equally likely outcomes also. Then your formula that you need to fill into your handout there is the probability, P of E is the probability of E equals, you're going to create a fraction. The numerator should have the number of outcomes in the event E, or in other words, the number of ways that E can happen, over the number of outcomes in the sample space. Or you can also think about it as the number of total possible things that can happen. Now, when you're working these problems, I'd like you to try to express this fraction in terms of the words. Try to write out what each number would be, like in words. What are you looking for in words? Because the more you can do that, as the problems get a little bit more complicated, then the easier it'll be for you to figure out what you're looking for. If you can express it in words, then you'll definitely be able to identify a value for it. Okay, the answer that you're going to get is anywhere between 0 and 1, or if you have that in percentage form, it's 0% to 100%. So if you get an answer of 0, that means that it is impossible for that event to occur. So it's not going to happen. If you get an answer of 1, or 100%, then that means it's absolutely certain that that event will always occur. If you get 1/2, then that means you have a 50-50 chance. In other words, it could go either way. It could go your way or the other way. And then if it's anywhere between 0 and 1/2, it's unlikely that event will occur. It doesn't mean impossible, but it's unlikely. And if it's between 1/2 and 1, then it's more likely that event will occur. Now, it's possible it won't occur, but it's got a better chance that that will happen. So if a die is rolled once, find the probability of getting a number less than 5. So we're looking at a 6-sided die here. And so if we're looking for the probability that we'll get a number less than 5, then I want you to think about what this means in words first before you try to figure out the answer. Okay, so the event of getting a number less than 5, we're thinking of that. The event of getting a number less than 5, that's our numerator. It can happen in 4 ways. So you could either get a 1, 2, 3, or a 4. So in words, you could write this out as, okay, the probability of getting less than 5, that's how you could write it out in shorthand there, means the number of ways to get less than 5, And then the denominator could be the number of total possible outcomes. Good. Okay, so the probability of less than 5 is the number of ways a number less than 5 can occur over the total number of possible outcomes. So that's what I want you to try to do, is try to write that out in words, even if you know the answer, because the more you practice that, the easier it's going to get when the problems are more complicated. Okay, so we just discovered how many ways it could happen less than 5, which was 4 ways, and then total possible outcome is 6. So that gives us 4 over 6, which reduces to 2 over 3. 95% of the problems you're going to leave your answer in the form of a reduced fraction. There will be a few times where we'll ask you for a decimal answer, but it's going to be very specific in asking you that. Okay, so 2/3 is bigger than 1/2, which means it's more likely that this will occur. All right, next question. You are dealt 1 card from a standard 52-card deck. Find the probability of being dealt a king. All right, so here's the thing. Some of you guys grew up with a deprived childhood and you didn't get to play cards a lot. And so you're not really familiar with a deck of cards. Now, in your book, you do have this picture right here. And so it helps you to familiarize your set with a standard 52-card deck so that you understand what it is that they're asking you in the problem. So make sure that you are familiar with this. Notice that we have 4 suits. That's what we call them: hearts, clubs, diamonds, or spades. Every suit has an ace, so there are 4 aces. Every suit has a picture card. The book calls them picture cards. I know you might have grown up with the word face cards. Okay, but the picture cards are the one that actually have a picture of somebody on it or a face on it. And so there's a jack, queen, and a king for each suit. And then there's a 2 through 10 for each suit. So knowing this, if we're going to find the probability of being dealt a king, and again, that's somewhere in your book. I don't remember. Let me see if I can find the page if you need to. That's on page 624. Okay, so you can make a note of that, page 624. Okay, this is my long, drawn-out explanation. So let me go back to this blanks page here. If we're going to write this out in words, we're trying to find the probability of being dealt a king, and we were only being dealt 1 card. So we want, in our numerator, the number of ways you can get a king over the total number of possible outcomes. Just get used to that phrase. That's always going to be the denominator, the total number of possible outcomes. Okay, so how many ways can you get a king in the deck? 4, because there are 4 different kings in the deck. And what are the total possible outcomes when you're dealt 1 card? 52, because you can get any of the 52 cards dealt to you. So there's your initial fraction there. And now you reduce. Okay, 1 over 13, I heard? Should be 13. Okay, so 1 over 13 is your answer here. So the probability of getting a king is 1 over 13. Much smaller chance of getting a king than, remember our last problem was 2/3, so 1/13 is very small, much less than 1/2. Okay, empirical probability is different than theoretical probability. Empirical probability applies to situations in which we observe the frequency of an occurrence of an event. In other words, we're not guessing as to what happens, we are watching what is happening. So the formula is really the same as the other formula, but you are watching or you're observing. So the probability of an event would be the observed number of times E occurs over the total number of observed occurrences. So the number of times that item happens over the number of times this experiment is going on. Okay, so here's an example of empirical probability. There are approximately 3 million Arab Americans in America, and this circle graph shows that the majority of Arab Americans are Christians. Now this was, I believe, taken from the census a while back. Okay, so if an Arab American is selected at random, find the empirical probability of selecting a Catholic. So notice in the chart, it's separated into 4 different colors. We have this group is Muslim, that's more of a purplish blue. This maroon color are those that are Catholic. The yellow are those that are Protestant, and that light green there is Greek Orthodox. And in case you're not familiar, sometimes maybe these problems can be a little confusing if you're not real familiar with religion per se. But Catholic, Protestant, and Greek Orthodox are all Christian religions, okay, just different denominations. But they want specifically the probability of selecting a Catholic. So again, try to put your fraction into words first. So the probability of selecting an Arab American that is, okay, Catholic, so would be the number of ways of selecting an Arab American that is Catholic over, you could say total number of possible outcomes, or you could just say total of Arab Americans in America. Okay, either way you want to look at it. All right, so here's our solution. So the probability of selecting a Catholic is observed number of Arab Americans who are Catholic. Okay, in this problem I use the word observed because that's what the formula asks for, which was 1.26 million, divided by the total number of Arab Americans, which was 3 million. Notice that they're both in millions, so I don't really have to worry about that. It's just 1.26 divided by 3. So that gives me 1.26 divided by 3, which is 0.42. This would be the situation where MathExcel would say, you know, round your answer to 2 decimal places or to the nearest hundredth in this case. So we got an answer of 0.42, and you would type in the decimal. So conducting a survey or a census would be, and the information you gather from that, the probability of, would be empirical probability because you're basing it on what you observed from the survey or what you observed from that census or whatever it is that you're doing. All right, comparing theoretical versus empirical. A coin that is equally likely to land on heads or tails is called a fair coin. Empirical probability can be used to determine if a coin is fair. So, you know, we know what the probability of landing on heads should be, but is that actually happening? Is the coin, you know, giving an equal chance of landing on either one? Okay, so we got a quarter here. And so in order to determine whether this is a fair coin, I could flip it a few times to see what happens. Okay, so first of all, it has heads or tails on it. And one thing that we can think about is, let's say we're looking for heads. And so if we were finding the theoretical probability of landing on heads, well, how many ways can it land on heads? 1 out of how many total possible outcomes? 2. Okay, so it should have a 1/2 probability, you know, 50-50 chance of happening. So as I flip, okay, I got heads, tails, heads, tails. It's actually very fair coin so far. Heads, tails, heads, 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 heads. Okay, so we had heads, tails, heads, tails, heads, tails, heads, 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 something like that, okay? All right, so if we were doing empirical probability, we would base it on what we just observed on the coin flipping. Okay, so the probability of heads with our experiment here was, well, how many ways did we land on heads? Or how many times? Okay, 7. And how many total times did we flip it? 10. Okay, so we ended up with 7 over 10. Now it's easier to look at this from a decimal point of view. So 1/2 is the same as 0.5, and 7/10 is the same as 0.7. So notice that when we do this empirically, when we actually flip the coin, it doesn't quite come out to 0.5. However, me flipping it by hand 10 times, maybe that's not enough flips to tell whether it's a fair coin or not. So what's really nice about the website that I had lined up that's not working today is that it flips the coin for me 100 times. Then it flips the coin for me 1,000 times. And what tends to happen when we use the computer to flip the coin for us is that, let's say when we do it 100 times, we get 0.57. Still not quite 0.5. Then let's say we do it 1,000 times, we get 0.512. Still not quite 0.5. We do it, 10,000 times, we get 0.5001, something like that. Okay, this is typically what happens when you flip the coin more and more and more times. So again, if you're going to use empirical probability to see if something's fair, you need to make sure that if you've done the experiment enough times to show that we've done that, we've gotten a good picture of what's happening. So this thing that's happening as that probability gets closer and closer to 0.5, it's called the law of large numbers. So as an experiment is repeated more and more times, the empirical probability of the event gets closer to the theoretical probability of the event. If it doesn't, that's when you know that there's something wrong. So if that coin does not get closer and closer to 0.5, maybe I'm getting heads every time. Okay, could be a two-headed coin, not a fair coin. Okay, so there are things that you want to double check to see if it's actually meeting the theoretical probability. Now you will have problems like rolling a die, picking a card. Let me see if I can get you some of the other types of examples. All right, now here you might be flipping a coin, but notice that you're flipping a coin 2 times. So in the set, they have already listed all the possible outcomes for you. So you could get a head the first time and then a head the second time. Or you could get heads the first time and then tails the second time. Or tails the first time, heads the second time, or tails on both tosses. So they've listed out that sample space for you. So it wants to know what's the probability of getting a head on the first toss. Okay, probability of getting heads on first toss. Well, that means we're looking for the number of ways to get heads on the first toss over the number of possible outcomes. Okay, so I heard 2. So looking at our list, the only ways that you get heads on the first toss is the first 2 that are listed. Okay, the other 2 does not get heads on the first toss. So we have a numerator of 2, and the total possible ways that this can happen is 4. So 2 over 4, but then again, don't forget to reduce your fractions. So 2 over 4 reduces to 1/2. Notice it's very specific. Type an integer or a simplified fraction. Good job. Okay, you might have a chart Okay, so what they've done for you is they've shown that you're going to roll a die twice. So you're going to roll it once, see what answer you get, then you're going to roll it again, see what your second answer is. So they've shown you a chart of all the things that can happen. You could get a 1 both times, you could get a 1 the first time and a 2 the second time, or a 1 the first time and a 3 the second time, or you could get the 2 the first time and the 1 the second time, and so on. Okay, so they've told you there are 36 equally likely outcomes. You should be able to figure that out with the fundamental counting principle, though. Because how many choices do you have for the first toss? 6. How many choices do you have for the second toss? 6. Fundamental counting principle tells you multiply those together. 6 times 6 is 36 possible outcomes. So I just want you to see how all those sections sort of tie together there. It says find the probability of getting two numbers whose sum is 8. Okay, which combinations give you a sum of 8? 2 and 6, 3 and 5, 4 and 3, and 6 and 2. Okay, so 2 and 6, 3 and 5, 4 and 4, 5 and 3, and 6 and 2. Nice little pattern that you might notice here when you're looking for a sum of two numbers. All right, so how many times does this happen? 5 out of how many total possible outcomes? 36. Does this reduce? No. So you put in your answer as 5 over 36. Okay, I wish I'd been able to do some more examples for you, but remember that you have your tutorial buttons there. And there will be some charts where they don't total it for you. You have to figure out the totals.